Hello, hello, hello. How's everybody doing today? Bye, babe. Take care. Have a good day at work. Welcome to the lecture. Got a pretty good audience. Everybody check in if you would. Chat me up. Hey, Ken, good to see you today. Looks like we got a pretty good crowd coming in here taking a look at our audience. Looks like we got, holy cow, 7 people so far. Fantastic. Welcome to the show today. You know what? This is the 10th lecture of the summer semester. We are 3 weeks into this class, so we are over a third of the way done. You folks probably know that because we have our first exam coming in. Hey, what's up, Travis, Donnie, Han? Good to see you, Violetta. Good to see you, Kara Phelps. Fantastic, Alex Gromley. And of course, I got Madison G on the cell phone. If you want to chat me up, and you're a visitor for the first time, all you have to do is log in with your Google account and it will activate the live chat right beside the video. Let's see, to the, I think it's this way is what it'll be on your screen. And then after you log in, you can chat in the chat board. Or if you want, just go ahead and send me a text. You've got my remind number, my text number, and we can chat that way. But everybody needs to check in, tell me hello. So, here's the deal. We are 1/3 of the way through this semester, so it is just about exam time. I don't know if you've taken a look at the exam yet, but I just want to exam time. I don't know if you've taken a look at the exam yet, but I just want to exam time. Okay, here we go. All right, I got it fixed. Now it should be better. What about that? Is that any better? Go ahead and type in the chat bar if you would and let me know if we've got better sound. Can you hear me now? Can you hear me now? Yes. Okay. Fantastic. Thank you. Very good. All right. I learned something today. All right. So Kahoot's got that background sound, and I had to turn that off. So I see that that's a problem. Thank you very much. Okay. Is everybody signed up? Alex G, KBH, TBW, KLP, Madison G. Are you folks ready to play? Let's go ahead and get started. So what I'm going to do is go ahead and type in the, so we got 5 players so far. That's not a bad number. Let's go ahead and get started. Ready, set, and go. I'm sorry, I forgot that part. I forgot that part. I had to deactivate some of my devices for that to work. Okay, fantastic. Okay, so it looks like 2 people got it right. Let's see what we got. Madison G at the top, KBH. Okay, I see some of you didn't play. Is there a reason why? A technical reason? That's the only reason I would care. Okay. If you would, type that in the chat bar. Let's go ahead to the next question. Are you ready? I noticed that only one person responded that time. I'd be curious at the end of this to find out what the problem is. Maybe I need to set the question latency a little bit longer. Okay. If anybody has any feedback and wants to type it to me, they should feel free to do that. Okay. Zero answers. Okay, so I learned something today about trying to do a Kahoot. Apparently the delay doesn't work well enough for us to do that. So maybe I'll have to try another strategy next time. Okay, right, because all of you were trying and you were just having a little bit of difficulty. I wonder why. Let me see, let me check my stream health. I've got the stream that's, let's see, I'm doing low latency. Is the stream getting choppy or anything, would you say? Okay. Well, you know what? Let's just go ahead and go into our lecture. So, there seems to be a delay. My phone had the answer choice for question 3 up before the question was available. Okay, cool. Well, you know what? I learned today that there are some limits to doing live interactive stuff on YouTube. Obviously, the technology doesn't work quite perfectly enough to do that. So let's go ahead and get started on the lecture. Those of you who came in to see how well the Kahoot quiz worked, there you go. That's our test for today. I told you it would either be awesome or it would be awful. Actually, this was somewhere in between, right? It wasn't awful, but it just didn't work. Is it choppy right now? Okay. All right. It's choppy on. Is it still choppy right now even? It's smooth again? Okay, cool. Then let's go ahead and get started with our lecture. Okay, fantastic. Well, clearly what I was trying to do was jamming up my bandwidth. Okay, cool. So if you remember on yesterday, we were talking about sensation and perception. I suggested to you that we have areas in our brain that are responsible for processing the 5 different senses, right? We have these primary sensory cortexes. And I suggested to you that these senses get put together in these areas called association cortexes, which help us to combine individual sensory experiences into larger conceptual experiences and also allow our senses to work again. So we talked a lot about vision yesterday. Today I want to focus on the other four senses. So we're going to talk about each of these four senses, spend a few minutes. I just want to hit the high spots, and then I'll let you go into your book and learn some more of the details. So the first thing we're going to talk about is the sense of hearing. Now, if you'll remember, I told you that sensory neurons, their job is to transduce physical, chemical, or otherwise external energy into patterns of action potentials. And just like the eyes, your ears are responsible for transducing wave information. So sound and light travels in wave information. So just like your eyes, your ears are going to respond to wave information. So there's a picture right here that I've got up on your screen. It's kind of small. You may not be able to see it in great detail. If you open up your book to actually page 190, you'll see this picture and you can follow along. This is just for demonstration purposes. But what I want you to know is that these sound waves come in through your outer ear and they cause this little structure called an eardrum. It's about half the size of a dime to vibrate. This causes these little bones in your ear, the hammer, the anvil, and the stirrup to vibrate. And they actually magnify that vibration by about 20 times. And they cause this oval window in your middle ear to begin to vibrate, which causes the fluid in an inner ear structure called your cochlea to begin making waves. Now, running through this cochlea looks like a snail shape. It's wrapped up. It's about the size of a pea. If you unwrap it, what you're going to see is that it's a fluid-filled sac that has this thing called a basilar membrane that comes in and divides it right down the middle. And on this basilar membrane, we have these hair cells, and these hair cells send up little fibers. Now, when the oval window vibrates, it causes the fluid in the cochlea to begin making waves, which causes these hair fibers connected to the hair cells to begin to move. And this moving is interpreted by the brain as action potentials. All right, so if you'll see, we've got the basilar membrane here. You've got your hair cells located on it. Now, your book talks a little bit about interpreting basic sensory experiences, right? So you can think of loudness and pitch. Now, your book's going to talk about two theories of pitch that explain how we might perceive high pitches like altos and reeds from low pitches like tubas and bass singers and very white, deep bass people. And what they suggest is some people think that it depends upon how fast these hair fibers vibrate. So higher pitch sounds cause these fibers to vibrate a little bit faster, okay, which is interpreted as a higher pitch. But I looked around and did some research, and it seems like really that's what we would call the temporal code theory of pitch development. Let's see. Excuse me. Yep. The temporal coding. So pitch is related to the speed at which these hair cells vibrate. Faster equals a higher pitch. And then there's a place coding theory, which suggests that pitch is determined by which fibers in the cochlea vibrate. It turns out if you look at the cochlea, we have it sort of unrolled right here. Higher pitches are going to be closer to the oval window, and lower pitches are going to occur when the hair fibers up at the very end of the cochlea vibrate. So those are two theories about how pitch is determined by our hair cells. Right now, if you remember, yesterday we talked about distance perception, and we talked about binocular disparity. Each of our eyes sees a slightly different image, and our brain interprets that to give us the perception of depth. Well, the same sort of principle works with the localization of sound. So your brain is able to figure out where sound is processed based on two cues: how loud the sound is in each ear and the timing of when the sounds arrive. And your brain learns over time to interpret those patterns to tell you where in your field of vision objects happen to be based upon their sound. Okay, any questions so far about that? Now, I do have an incredibly interesting video that I think you'll find super duper interesting, and it's related to Ben Underwood, the gentleman who actually sees with his ears. And he's a great example of what we call neuroplasticity. He was born without his eyes, or not born without his eyes. He had to have them removed early in life. And so his auditory nerve sort of grew into his visual processing center. And just like you can use sound differences to interpret location, he used sound differences to sort of begin to identify shapes. Any questions so far? Let's talk a little bit about the sense of taste. Now, if you remember, I told you that the transduction in the eyes and the ears relates to physical energy created by waves, right? Light and sound waves. Taste is a form of chemoreception, so we record chemical information in our mouth. Now we have taste buds, it turns out, on our tongue, down our throat, and I even was reading that there's some sort of chemoreceptors in our lungs that respond to bitter. And so what we do with the sense of taste is we record chemical information. Now, if you look inside your tongue, you're going to notice that you have bumps, different sized and shaped bumps around your tongue. Those are called papillae, and you have, I'm not sure, a limited number of them. You'll see if you look at the tongue picture down here at the bottom right of the screen, you'll see the bitter, those green circles, those are papillae. And in those papillae, we have taste buds. And inside your taste buds, you have taste receptors. And taste receptors are responsible for perceiving chemical information. Now, I was reading, it turns out that we have primarily bitter and sweet taste receptors. And your book doesn't exactly, actually the state of research doesn't exactly know how salty and umami are actually processed by the brain. But it turns out that you have chemical receptors that respond to different chemical molecules, and these give us the 5 basic experiences of tastes: sweet, sour, salty, bitter, and umami, which I would call savory, like pot roast with mushrooms. I guess that's how they explain that taste. Now, I was actually reading up on taste, and it turns out that not all mammals have the ability to taste all of these different sensations. So apparently, if what I read is true, cats do not have the taste receptors to experience sweet. And panda bears, which evolved from meat diet to a bamboo diet many millions of years ago, they actually don't have receptors that allow them to process the taste of umami, right? And so what happens is you have these taste receptors on your tongue. This information is transmitted up through your thalamus to your gustatory cortex, located in your cerebral cortex, in the frontal lobe of your cerebral cortex. Okay, Now, some of you might be picky with your food. Some of you maybe don't like coffee or chocolate, or collard greens make you gag. It turns out you may be what they call a super taster. And there's an example in your book. If you want to figure out whether or not you're a super taster, do the little experiment on page 198. But apparently one of the differences between people who are super tasters and people who are medium tasters or low tasters is they have tons more taste buds in their tongue. I think it's 6 times the number of normal taste buds. So I invite you to try the demonstration on 198 to figure out if you're a super taster. Now, I love dark chocolate. I absolutely love coffee and collard greens, so I'm going to assume that I am not a super taster. Any questions so far? Any questions so far? Wow, we got 12 people watching so far. Thank you very much for coming to my lecture today. If you like this lecture, go ahead and go ahead and follow my channel, become a fan, whatever that is. I don't even know what that's called. Subscribe to my channel, and you'll get reminders so that you won't miss any of these lectures. Sorry about the shameless promotion. All right, now, here's the deal. The sense of smell is also a form of chemoreception. So just like taste, our sense of smell processes chemical molecules. So apparently in your, let's see, what is it called? So inside your nose, you have this olfactory epithelium, and you have these, your olfactory receptors kind of stick out of this olfactory epithelium in the top of your nose, this mucus-covered layer of cells, and you have these chemoreceptors in there that respond to individual molecules. And I think I was reading, and it looks like I think you have maybe 1,000 different molecule sensors in your nose, right? And what happens is these sensory receptors, these olfactory nerves, transduce molecule messages into action potentials. Now, you folks have always heard that that human beings don't have nearly as good a sense of smell as do dogs. It turns out it's for 2 reasons. You do not have nearly as much olfactory epithelium in your brain. I think you have, I think what they said was 1.6 square inches of olfactory epithelium in your nose, and a dog has 26 square inches of olfactory epithelium in their nose. So they have more square area of area to be innervated, and also they have a more densely packed. So not only do they have more epithelium, but they have more olfactory receptors per square inch. And so that's why dogs' sense of smell is so much greater than ours. So you have these olfactory receptors in your nose. They transmit information up through from this olfactory epithelium into the olfactory bulb, which combines you. So you have different receptors. You have the same receptor spread all over your epithelium. And so what happens is all of those different receptors that code for the same scent are combined together in your olfactory bulb. So you may have a grandma's apple pie receptor here, 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 here in your olfactory epithelium. All of those are going to get the same molecule smell, and so the number of molecules is sort of going to give you a measure of how intense the smell is. All that's collected in your olfactory bulb, which then transmits the information up to your olfactory cortex in the frontal lobe. Remember, this is the only conscious experience. This sense is different from the others in a couple of different ways. Number one, it's the only sensory experience that doesn't go through the thalamus. Remember, we've talked about the thalamus several times. And number two, there are a lot of connections between smell and our amygdala and the entorhinal cortex, which is in our temporal lobe, our memory center. And so this may explain why smells evoke such memorable experiences and take us back to our childhood. So you may smell spaghetti or fried chicken and think about your days at grandma's house. I remember I was watching, who's that chef? Gordon Ramsay. he was cooking a beef Wellington. I've never tried a beef Wellington, but I do cook and I like recipes. And he was cooking a beef Wellington, and he was talking about how beef Wellington smelled like Christmas to him. And so apparently he'd had it back in those days of Christmas, really good times. And so this memory, this smell is associated with a feeling and a memory from way back in his days. So smell, it's really connected to your memory, and it also isn't processed through your thalamus. Any other questions? Any questions so far? So let's see, we talked a little bit about so light and so vision and hearing relate to waveform energy. Smell and taste respond to chemical energy, and your sense of touch is responsible for what we would call mechanical energy. So you have mechanoreceptors. And your skin is filled with sensory neurons that record pressure, pain, and heat, and then transmit this information up to your primary sensory cortex, which is located in your parietal lobe. Now, we have different types of sensory neurons for touch. We have warm receptors, we have cold receptors, and we also have 5 different types of pressure receptors. So you have receptors that tell when the hairs on your skin are moving. You have receptors that measure vibration. You have pressure receptors that measure light, fast pressure, light, slow pressure, and even stretching, whether or not body parts are stretching. Because one of the things you need to do in order to move yourself around is you need to be able to feel your body parts so you know what shape or what movement they're engaged in, okay? Now, I didn't mention this, but if you think about it, one of the sensations that we do have when we eat food, not only do we have a sense of taste, but you also have a sense of warmth in your tongue well. So you have sensory neurons in your mouth too. If you've ever eaten those mashed potatoes that are 4 million degrees Fahrenheit, you know what I'm talking about when I tell you that you have heat receptors in your mouth as well. Or maybe you don't like cold food because it's kind of tastes nasty. I happen to like cold steak. I don't know if any of you like cold steak, but it may be because, you know what I mean? So you do need to keep in mind that you have sensory receptors also in the areas around your nose and mouth too. So, your warm receptors, your cold receptors, and some of your pressure receptors are going to travel up your spinal column into your primary sensory cortex, and they're going to allow you to consciously feel the parts of your body. And we mentioned this in chapter 2, but I'm just going to reiterate it, okay? If you remember, when I touch my right cheek, somewhere in my left sensory cortex, I feel that. I consciously know that I've been touched. And you'll see that each body part is mapped out. The conscious experience of touch for each body part is mapped out on the primary somatosensory cortex. And I'm going to reiterate again that the area on the somatosensory cortex doesn't depend upon the body part size, but the complexity of its action. Notice how much space is there for lips compared to the space that there is for your entire arm. It's because your lips do really complex things and your arm just goes up and down or moves back and forth like that, okay? So I do want you to know that, conscious touch. Now you also have what we would call a kinesthetic sense. So a lot of your neurons are going to innervate your muscles in your joints, and they're going to allow us to tell what kind of pressure you have on that joint. So how much are you lifting? How much weight do you need to give back? It's going to tell whether or not joints are stretched, so you'll be able to gauge relative position of the body parts. And so you're going to have nerves that actually, instead of going to your sensory cortex, these are going to go to your cerebellum. think about this as sort of your non-conscious touch. And this goes to your brain, which helps your cerebellum, which helps you move around because it feels where your body is so it can organize movement. So your cerebellum's going to feel the pressure on your feet when you walk. It's going to feel the pressure on your knees. When you write, the cerebellum's going to feel the pressure and grip in your hands. It's going to get all of this information through stretch and pressure receptors. And then finally, we all have the experience of pain, which is noxious touch, if you will. And so it turns out that conscious touch, feeling like tickle and pressure are carried on one set of neurons, but you have a completely different set of neurons that respond to pain and injurious experience. Okay, and so one of the things that I did want to mention your book talks about is the speed at which a sense of touch gets to your brain depends upon how thick the axon is and whether it's myelinated. So neurons that are thicker and more myelinated are going to transfer information to your brain much more quickly than axons that are thin and unmyelinated. Okay, a good way to see this difference is in the fast and slow fibers associated with pain. All right, so you have fast fibers that are thicker and myelinated, and they tell you about quick, sharp pains that you may feel. And if you think about it, that's useful because if it's a sharp, super acute, painful experience, you need to get away from it as quickly as possible. But if you're like me and you've got 50-year-old aches in your back, or you went out and walked too much and your knees just kind of aching and sore, that pain information is actually being transmitted on slower fibers, which are thinner and unmyelinated. Okay, so it's going to be, when we talk about touch, more than any of other senses, because most of the other senses occur in and around our head. Taste, smell, vision, and hearing all occur in and around the head, but touch can occur from all over your body. And so speed at which you get information to and from your brain is very important. And so things like tickling, they travel really slow, but feelings like light touch, pressure, and jabbing pains, those transmit much more quickly to the brain than do these other sensory experiences of touch. Okay, so that's all I wanted to talk about today. I want you to know in which cortex each of the five senses is processed. I want you to know exactly what the receptor cell types are in each of these five senses. So I want you to know rods and cones are vision, hair cells are hearing, olfactory receptors are for smelling, and I want you to know which ones respond to wave energy, which ones respond to chemical energy, and then I gave you a couple of factoids along the way about each of these senses. Does this tell us not to grip an egg for not as hard as a baseball? I'm sorry, I was lecturing, didn't even get your note. Does this tell us not to grip an egg, for example, not as hard as a baseball? You know, I've never thought about the neurological reason for why we should do that, but I do remember my coach telling me to do that. I think it's because if you've got the hands, the muscles clenched, you can't be as flexible, right? Hold it like an egg. Are you trying to quote Bull Durham from the 80s? Are you showing your age, Ken? You probably are. Okay, so that's really all I had to say today. I am so sorry for the lack of smoothness in today's lecture. So was this lecture pretty jumpy today? If somebody could please chime in real quick and give me a little bit of feedback, I'd be curious, because my live streaming indicator was showing that some of the talk was not as smooth as it should have been. Right. Yeah, it looks like we got about a 10-second lag going on. All right, well, I tell you what, that's really all I wanted to say today. It's been great talking to you. Remember, tomorrow we have lab class in Microsoft Teams. Don't forget to watch the video, Nadine Burke-Harris's talk about ACEs. We're going to talk about childhood trauma and how it relates to our physiological development and well-being. All right, so I really hope you watch that video. Come to class tomorrow, and you know what, we'll actually talk about quarter life identity crises just like we did on Tuesday. We'll see if any of you are having quarter life crises and what that's all about. All right, cool. Well, you know what, have a great day, and I look forward to seeing you tomorrow in lab at either 10 a.m. or 1 p.m. Take care.
Your call cannot be completed as dialed. Please consult your directory and call again, or ask your operator for assistance. This is a recording.